Sir, your mic is off, sir.
I'm sorry. Uh, when did it stop? Just now or hello?
Sir, before that it was off, sir.
From the beginning it was off.
Not from the beginning, some middle, sir. Just the moment when you started drawing this T1, T2.
Yeah. Thank you for clarifying it. See,
Yes, sir.
what I'm doing is I'm taking a simple slab here. On the slab, I'm taking this temperature T1 on one side, T2 on the other side, and the thickness of it is L, and the material is having a thermal conductivity, and this thermal conductivity is not a constant thermal conductivity with respect to the temperature. That is, with respect to temperature, this thermal conductivity is varying. That is, what I am doing is K is taken as a function of temperature. So K is going to vary with the temperature. That's what I am going to consider here. If this is the case, what is my governing equation? What is my governing equation I want to write? So if I take my governing equation in this case, so how it will be like? See, what I'm doing here is I'm assuming that it is one dimensional, Qgen 0, and the steady state case. If this is the case, what will be my governing equation? Somebody please tell me. What is my governing equation now? D by dx of K of t into dt by dx is equal to 0. So how did I get this? Let me go to this equation. If I go to my equation, this is how my equation is. Okay. In this equation, you have considered that k is constant. That's why you have taken out the k as a constant and you have put it here. Okay. But if this is not constant now, what happens is it has to come here. Okay. Let me do it this way. This is my equation actually. Okay. In this equation, what I have done is I have considered that this k is constant. That's why I have taken it as a constant and then multiplied it. But this k will not be here. This k will be inside this derivation. Okay. So that's why I got this inside the derivation here. Okay. So here, since this is one dimensional, these two with respect to y and with respect to z it is 0, and the qzen is 0, and steady state this expression will be 0. When these three expressions are 0, then what I am left out is left out as d by dt, d by dx of k of t into dt by dx is equal to 0. Okay? This is what I have as my governing equation. If I have a governing equation with me, what I should do next step? I should integrate this. When I integrate this, what happens is integral d by dx of k of t into dt by dx, I will get is equal to 0. That will be k of t into dt by dx is equal to some constant I will get. So this is how my expression will turn out to be. Now, what I have to do, I have to integrate it further. When I integrate it further, what I do is I will do something called as variable separable. K is function of t into dt I will write this side, and dx I will write on the other side of the equality, that is this side. Now, I'll integrate it, but When I integrate now, I will integrate with the limits. That is, I will take the definite integration. Okay. When I integrate it with limits, see the temperature here in the case that we have considered, it is varying from T1 to T2. Okay. And then X, it is varying from 0 to L. This is 0, this is X is equal to 0, this is X is equal to L. Okay. Forget about this L1, it is simply L. Okay. So its X is varying from 0 to L. So what I will do now is, I will take this one with the limits, that is, this is taken from T1 to T2 into K of T into dt is equal to integral. This is taken from 0 to L into C into dx. This is what I will take, and then what I get here is, on this side, I will leave it like this only, integral T1 to T2 into K of T into dt. I will leave it like this. On this side, I'll take the integration. I'll keep C aside, and I will take integral dx. Integral dx is x, and it's varying from 0 to L. These are the limits. So this one is integral T1 to T2 K of T dt is equal to C into L minus 0, I will take. Okay. So what I will get from this is C value is equal to 1 by L into integral T1 to T2 into K of T dt. I will get. I will keep it aside, and then I will write from Fourier's law of heat conduction. Fourier's law of heat conduction, that Q is equal to minus Ka into dt by dx. That's what I have. But here what I will do is, I will take K as a function of temperature. Simply, I will not take just K, which is a constant value. What I will do is, I will take K, which is varying with respect to temperature. Ka into dt by dx I will consider. Okay. Now, see here, if you look at this, this is, let me call this as something like A. We call this as A. If I substitute A into this B, substitute A in B, if I do that, what I get is Q is equal to minus of K of T into dt by dx is actually your C. Okay, so that's what you have in your equation A. So that I have substituted here. So what I get is Q is equal to minus A into C. Okay, now I'll call this equation C is equal to something is there now. I'll call this as equation C, and this is equation D. Sorry, D. Now what I'll do is, I'll substitute that C in this D. When I substitute that D into this, that C into this D, what I get is Q is equal to minus of A into, in the place of C, what I got is integral T1 to T2 K of T into dt. That's what I got. 1 by L into integral T1 to T2 K of T into dt. So I have missed this 1 by L here. Okay. So if I have to write Q here, the Q is, see this minus I am taking inside. When I take it inside, what happens is A by L, I can write it. The limits will reverse. That is, instead of taking T1 to T2, I have to take T2 to T1 because I am taking this minus inside. So the K of T into dt, I'll get. Okay. So this is your expression for calculating Q. Expression for calculating Q when you have a temperature dependent thermal conductivity. When you have temperature dependent thermal conductivity, this is your expression for Q. Okay, where K of T is given as a function of temperature. So that's all. At this level, do you have any questions? If you have any questions, please ask. Right. Now that's right. Let me move forward. Let's solve the problem now. When I solve the problem, you will get this even more clarity. See the problem, I have put that in your Google Docs. You may refer to your Google Doc for the same. So this is your question. So in this question, what is given is, he has considered a slab problem. The slab problem, what he is doing is saying that the K of T is K naught into 1 plus beta T. That's what is given. And K naught being the constant thermal conductivity and beta being the temperature quotient of thermal conductivity. And he's asking you to develop an expression for the rate of heat flow Q through the area of the slab. Okay, let's do the problem till here, then we'll come to the remaining part. Okay. So first we'll complete this, then we'll complete. So what we have till now with us is Q is equal to A by L into integral T2 to T1 into K of T into dt. This is our Q expression when your thermal conductivity is varying with respect to the temperature. Now, that's what the problem is. That's why I have taken this expression here. Now, K of T is given as K naught into 1 plus beta T. That's that expression I will substitute here. K naught into 1 plus beta T I have substituted. And then I have said dt. Now, if I take it, what happens? A by L will be on one side, and I'll take the integration into it. So the K naught is also a constant thermal conductivity as it is given in the question. As it given in the question, it's a constant thermal conductivity. So what I can do is I can take K naught out of the integration and put it aside. And when I take integration T2 to T1, our first expression is 1 into dt I will have, plus beta is also a constant, so I can put beta also outside of the integration into T2 to T1 T dt. So this is how my integration will be like, and if I further take the integration into it, a by L into K naught into integral dt is t. Now I am applying the upper limit and lower limit into it, plus beta into integral t dt is t square by 2. So this I have to apply my upper limit, then the lower limit. Now a by L into K naught. And if I do this here, it is T1 minus T2 plus beta into, if I do this here, T1 square minus T2 square by 2. So what I can say is, I can say that this Q is equal to this whole thing is my expression that he is asking me to find in the question. See, what he is asking me to find in the question is, he is asking you to develop an expression for the rate of heat flow Q through area A of the slab. So for that, what you will have is, this will be the expression. Okay, this you can directly use as a formula, or you can derive it for yourself. My suggestion is, you remember this formula. As far as temperature dependent thermal conductivity is concerned, you remember this formula. When you remember this formula, you can derive whatever the case he has given. He need not give you K is equal to K naught into 1 plus beta T. He can also give you like K of T is equal to K naught into 1 plus beta T plus beta into T square plus beta into T cube plus so on. The expression can be very long. Okay, so based on the K of T, how K is varying with temperature. It need not be a straight line variation that is given in the question here. It can be a quadratic variation. So it can vary in a curve form. So that can also be the case. So based on that, you have to consider this K of T and then solve for your Q accordingly. And this Q will vary with respect to the case. Right. So that's all about the developing expression. That is the first part of the question. Now let us move to the second part of the question. This part. What is given is given that the L value is 0.18, and then let me put that question again over here. Remove. What I have here is just this part. This is a question given to you. This is actually beta. Its slab has so and so thickness. This thickness is given. And its temperatures on one side and the other side are given. Calculate the heat flow rate per unit area is giving you, and K naught is given. So what is giving you is giving you all the things that are required for calculating Q in this formula. Okay. So L he has given, A he has given as 1 meter square. It is shown here 1 meter square. And then K naught is given, it is 0.2 watt per meter Kelvin. The beta is given 2 into 10 to the power minus 3. See, this beta will have Kelvin power minus 1 because beta is multiplied with temperature, and then K of T is equal to K naught into 1 plus beta T. See, this K naught is also having the same unit of K. So this should not have any unit. This should have 0 unit. That is the temperature unit and beta unit should get neutralized. K power minus 1 here, K here. So both will get cancelled and you will not have any unit. So the beta unit is K to the power of minus 1, where beta is a coefficient of thermal conductivity, temperature coefficient of thermal conductivity. So that's the beta story. So the T1 value and the T2 value. T1 is 500 Kelvin and T2 is 300 Kelvin. So you have to appropriately consider all the data that is given here, and then Q you have to substitute into this equation. Area is given as 1 and L is given in SI units itself as 0.18 and the K naught value is 0.2, and the T1 minus T2 is 500 minus 300 plus the beta is 2 into 10 to the power of minus 3 into 500 square minus 300 square by 2. So now you tell me what is the Q value. Please calculate and tell me
400 watt
the
per
value.
meter square.
What is the value?
400 watt per meter square.
400 watt per meter square Kelvin. Per meter square Kelvin.
Sir, only watt per meter square.
Watts? Why per meter square is there? You need not have per meter square because the area is there here. Area is
Oh,
on.
yeah, yes, sir, yes, sir. Yes.
It is
I mean,
simply watts. So what you get here is simply
yes,
watts.
only watts.
400 watts is your answer. Okay.
Sir,
Sir, you're not audible, sir.
sir,
Give me a minute.
Check. Am I audible now?
yes, sir.
Yeah. Thank you for confirming it. The lead seems to have changed today on my cell phone. That's why these things. Okay. Anyways, so now what we will do is we'll consider a cylinder here. I'm drawing the cross section of a cylinder here. So this is a cylinder, and in this cylinder there are temperatures T1 and T2. Here I have T1 on this side, and here I have T2 on this side. So I will consider the radiuses here. This radius I'll call it as A. This radius I'll call it as B. You can call it as R1, R2. It's up to you. But now I'm calling it as A and B. Now, if I have to take the governing equation, how the governing equation will be like here? Can somebody tell me what is the governing equation here? Yes, somebody please respond.
One by r d by dr of r dt by dr.
Hmm. Correct. Uh, right. This is your equation here. In a cylindrical coordinate system, the expression is like this. What I'm doing is I'm considering a 1D problem and Qgen is equal to 0 problem and steady state problem. If it is steady state, this expression will go to 0, and Qgen, this expression will go to 0. Because it is 1D, that is R is only there, theta comma Z. Theta and Z are not considered. Theta and Z I will take it as 0. And whatever K is there here, this K cannot be taken out here because K is varying. So K should be taken inside here. Okay, this expression is nothing but your R into dt by dr. Okay, so if I write it, what it will be like is d by dr of R into the K of t is taken inside your derivation, and dt by dr into, yeah, this is equal to 0. Anyways, 1 by r will be there here. This 1 by r will get equated to 0. This 1 by r will become 0. Okay. So this is your governing equation. Now this turns out to be your governing equation. Okay. And this governing equation you have to take, and you have to transform this governing equation the way you have transformed it for your slab, and you have to get the expression for Q. So how do I do that? For doing that, I'll integrate it first. When I integrate that, what happens? D by dr will go out, and R into K of t into dt by dr will turn out to be some constant value C. So that's how your C will be like. Okay, that's how the C is. Now that you got C, then you integrate it again by doing variable separable over limits, over the limits given. Okay, what are the limits given here? The limits given here are for temperature, it's varying from T1 to T2, and as far as radius is considered, it is varying from A to B. So now, if I take the variable separable here, what I get is K of T into dt on this side, on the other side C into dr, and 1 by r you will get here because of this r. So this is the thing, and when I integrate it here, the limits here will be T1 and T2. The limits here will be A and B. Okay, so this is your integration form. When I integrate it, what happens on the Left hand side I leave it as it is, like I have done in the previous case. K of t into dt is equal to c, anyways it will be there aside. What is the integral 1 by r dr? It is log r. So natural log ln r I am taking, that is log to the base e I am taking, and I will have here b and a. So if I further substitute the limits into the ln here, it is b by a I'll get. It is ln b minus ln a, which is log b minus log a is log b by a. So that's what it is. So from this, what I'll write is, I'll write what is called as c, which is equal to ln a by b, or I can write it like ln b by a. On the other side, you'll get into integral t1 to t2 you will have, and then sorry, k of t into dt. This is your C. Okay. Now, from Fourier's law of heat conduction, Fourier's law of heat conduction, what I can write? I can write the expression for Q. Expression for Q will be k into uh, sorry, k of t. See, k a dt by dx. So simply you cannot write here. Okay, k dt by hello. Am I audible?
Yes, sir.
Yeah, thank you for confirming it. So here, what I have to do is I have to take Q, like your Q is equal to 1 by 2 pi KL. That formula is there now. According to that, I have to take Q is equal to 1 by 2 pi KL. 1 by 2 pi KL is taken for resistance. So what I have here is 2 pi KL into the ln dt by dr. So what I can write here is, in place of this 2 pi KL, I'll just transform this. This is minus 2 pi r into L into k of t into dt by dr I'll get. Okay, this is how your expression will turn out to be. And what you have next is, you have to take this k of t into dt by dr as c. What is c? This is, let me call this as a, let me call this as b, and substituting a into b, what I get is q is equal to minus 2 pi rl into this r. I think I've gone mistake somewhere. Yeah, this r should be taken inside. This r will not be there here. 2 pi l, r is actually inside your a. So what I get is simply c here. 2 pi l into c is the expression that you are going to get here for q. Now that you got it for q, you also have the expression for c here. C here is, let me call it as equation c, and let me call this as equation d. When I substitute c into d, substitute c in d, what I get is q is equal to minus 2 pi l into the c value is 1 by ln 1 by ln b by a into the integration T1 to T2 into K of T into dt. So that's the expression I have, and this will turn out to be your expression for your Q. In case of a cylinder, Q is equal to 2 pi L by ln B by A into the integral. See, I have taken minus inside, so this will be T2 to T1 and K of T into dt. And this will turn out to be your expression for cylinder when there is a variable thermal conductivity. Okay, so that's all for today. Let's go to the attendance.